ladies and gentlemen. In our previous lecture, we talked about vector spaces, and basically we looked at a vector as that given non-empty set that is defined over a given field F and that holds or satisfies given axioms. We basically talked about 10 axioms that must be satisfied for any elements picked from a given vector V and for scalars picked from a given field F. And basically, we talked about axioms of addition and axioms of scalar multiplication. Under addition, we looked at properties or axioms such as closure and addition, commutativity and addition, associativity and addition, additive identity, and additive inverse. We basically talked about axioms that are related to scalar multiplication, where basically we talked about closure under scalar multiplication, we talked about distributive property, we talked about associative property of multiplication, and multiplicative identity property. So we talked about all these 10 axioms here that should be satisfied for a given non-empty set to be called a vector space over a given field. In our previous lecture, we talked about some of the examples of vector spaces. And if you recall very well, we talked about this space, k to power n. So when you are looking at a given space to show that it is a vector space, majorly you must first of all look at the vector addition and scalar multiplication. Because when you look at other axioms, they are axioms which are actually under vector addition and scalar multiplication. So after knowing these two axioms here, they will help you to prove the remaining other axioms. Because the most important thing is to know how to add. If you pick any two vectors, that is, for example, u, which is in the form a1, a2, up to an. You also pick another vector v, which is in the form of b1, b2, up to bn. We looked at the elements in this space here, k to power n. They are n tuples. They are in this form here. So you need to look at how best can you add u plus v. How best can you add this? It is a matter of getting the addition of the corresponding elements. A1 with B1, A2 with B2, AN with BN. So if you are able to define the vector addition and scalar multiplication of a given space, then it will help you to get all the remaining axioms. So basically, at first we are looking at these main axioms. We are basically talking about, if you are looking at a given space, how do you define the vector addition and scalar multiplication? Because with that, with this definition of vector addition and scalar multiplication, and knowing what a zero vector or a negative vector, how we can treat them, you can easily prove the remaining axioms. Because when you look at how we defined a vector space, when you look at how we defined a vector space here, you look at majorly we have axioms classified into two. That is axioms of addition and axioms of scalar multiplication. So to prove that a given non-empty set is a vector space, then you must first of all know how to deal with the addition of vectors in that given space and how to deal with the scalar multiplication. Then all others, you can easily see that all these others are defined after knowing how to add the two vectors. For example, after showing that u plus v is still in v, that is the closure and addition, you can easily prove the commutativity, associativity. You can easily talk about the identities and the inverse. Also, when you talk about the scalar multiplication, if you define that you can easily multiply a scalar with any given vector picked from V, then you can as well look at the distributive property. You can easily talk about associative property, and you can easily talk about multiplicative identity. So that's why when we are looking at these examples, we are majorly focusing at defining the vector addition and scalar multiplication, because with that you can easily prove the remaining axioms. So in our previous lesson, we talked about this space Kn. We also discussed its vector addition and scalar multiplication. So which I believe at the moment it is very okay with us all. So we also talked about the polynomial space P of t, and basically we know how to add given polynomials. You know how to deal with the scalar multiplication of polynomials. So we talked about this polynomial space as well. Now we need to talk about this polynomial space Pn of t, but it is more related to the polynomial space that we looked at in our previous lecture. So with this one here, basically we are looking at Pn of t, and Pn of t, we are simply saying that if you consider P of t, that is a polynomial which is picked from this space, if we have P of t which is in this given space P of n of t, then which is of the form a0 plus a1 of t plus a2t squared up to ast to power s. But here we are talking about the power s, or this last value here. This value here should be less or equal to n, meaning the degree. We are talking about the degree of s to be less or equal to n. That is for finite case now. So if we are looking at P of t, that is having polynomials stopping at some given value, that is for s less or equal to n. It means if s is equal to n, then you are talking about a0 plus a1t plus a2t squared plus up to an of t to power n. The n can be any degree, it can be 2, can be 3, 4, 5, n degree. So basically we can easily define also the operations of addition and scalar multiplication using the same format we did in our previous polynomial space. In other words, we use the usual operations of addition on polynomials, how to add the polynomials, we dealt with that, and we also deal with the same way we deal with the multiplication of a polynomial by a constant, or what we can call a scalar. So this one here is more of the same as that one that we talked about in our previous case, that is about the polynomial space P of t. Let us talk about the matrix space, which we can denote by M of Mn. In other words, this is a space consisting of all M by N matrices. So when we talk about M by N matrices, we are talking about a 2 by 3 matrix, a 3 by 2 matrix, or a 4 by 5 matrix. So long as it is an M by N matrix. Then if we look at the space that is consisting of such matrices, then under what conditions can we say it is a vector space? So majorly, if we can easily look at addition and scalar multiplication, if we are able to define these two, we can easily as well prove the remaining axioms. But basically we need to understand how do we deal with the addition of matrices and scalar multiplication in matrices. So when you have, for example, a space which is consisting of 2 by 3 matrices, if we have such a space M, which is consisting of 2 by 3 matrices, then this space here, for example, we can say that is A and B, for example, picked from this given space. So if vector matrices A and B are picked from M, of which A is of the form, for example, A1, A2, A3, A4, A5, and A6, and B is also of the form B1, B2, B3, B4, B5, and B6. That is a 2 by 3. So you can easily define A plus B, and you know that when we are adding in matrices, we add the corresponding entries. So A1 will be added with B1, A2 will be added with B2, and A3 will be added with B3. So likewise, A4 will be added with B4, A5 will be added with B5, and A6 will be added with B6. So what you obtain here, you can clearly see that these entries here are real values. So which means when I add A1 with B1, I can easily get a value here. When I add A2 with B2, I can easily get a value. And the overall will be a matrix which is as well a 2 by 3 matrix. So in other words, when you add a 2 by 3 matrix with a 2 by 3 matrix, then you will as well get a 2 by 3 matrix, which means that that same matrix will be within that given space. So when you talk about a 2 by 2 matrix, when you add a 2 by 2 matrix with a 2 by 2 matrix, you will get a 2 by 2 matrix, which means that that result or that value that you have obtained, which is a 2 by 2, will still lie within that given space of 2 by 2 matrices. So that's why we can easily define addition of matrices within this given space, and scalar multiplication is as well possible, because when you talk about, for example, 2 multiplied into A1, B1, A1, A2, let us use this matrix, A1, A2, A3, then A4, A5, A6, then the result here will be 2A1, 2A2, 2A3, 2A4, 2A5, 2A6. So you realize that even after multiplying 2 or this given scalar into this matrix, we still remain with a matrix which is a 2 by 3 matrix, which means this one here will be within a matrix space which is of 2 by 3 matrices. So clearly we can easily define a scalar multiplication operation onto the matrix space. So when we have matrices of, for example, this order m by n, then we can easily say that M, which is a matrix space of such matrices, will form a vector space under usual operations of matrix addition and scalar multiplication of matrices. So basically, we can easily define the two operations, which two operations can help us to define the remaining 8 operations. So if we are talking about an m by n matrix A plus B, this is how we define the addition of the two matrices, and this is how we define the scalar multiplication of a scalar with a matrix. And you can easily see that even the result or the matrix you will obtain will as well be in that same space. Let us now talk about the function space f of x, and we shall say Suppose X is our non-empty set and F is our field. Then we can denote f of x to be the set of all functions of x into f. So if we have functions within this given set that take elements of x into f, then we shall be as well saying that this f of x, this given set, will also be non-empty, since our x is also non-empty. Then we shall be able to define f of x as a vector space over the given field f under the following operations. 1. We shall talk about vector addition. How do we add two functions from this given set here? So if, for example, we have f and g, which are functions of this given space, then we can easily get f plus g, which is operating on the elements of x, which is operating on elements of x. So it can easily operate on element x. So we are looking at x, which is picked from the set x. So when f plus g operates on element x, then it will be same as someone who is getting f of x plus g of x. And this is applicable for all values of x that are picked from the set x. So in other words, having f plus g operating on an element x, it will be same as getting f of x, that is f operating on x, plus g operating on x. So we can easily define the vector addition. When we talk about scalar multiplication, if you have a scalar k that you have picked from the field f, and you have f which is picked from the given set f of x, then we can have a scalar operating on this given field. So if we have kf operating on x, element x, which is picked from the set x, then this is same as having k then times f of x. So having kf operating on x is same as having k times f of x. Similarly, we shall define the zero vector in f of x, and zero vector will be that zero function which is mapping elements of x into the zero element which will be in f. So this is same as having a zero operating on an element x, which x is picked from x, and this zero function here will be mapping all the elements to 0. And when you talk about the negative function, especially if you want to talk about the inverse, to show that there exists an inverse, then you need to know about the negative function. If you need to talk about the additive identity, then you also need to know about this negative function. So to talk about the negative of f, so we obtain negative of f by simply, when we talk about negative f of x, it will be same as talking about negative f of x. So having defined a vector addition and scalar multiplication on this set here, which is f of x, we can easily prove all the remaining axioms and show that f of x is a vector space. Let us now talk about some few examples on how to prove that a given set forms what we call a vector space. We shall look at question number 2. Question number 2 says a set of elements r to power n, which are of the form x1, x2 up to xn, for which we are picking xi from a set of real numbers for all the i's, meaning that x1, x2 up to xn are real numbers. and we shall define this set under the operations of addition. That is, if we are having any element of r to power n, that is x1, x2 up to xn, then we add there another element of r to power n, which is y1, y2 up to yn. It will be same as adding x1 with y1, x2 with y2, xn with yn, as defined here. So it is clear that xi and yi are elements of the set of real numbers. Then the scalar multiplication, if we have an element of r to power n, which is having the form of x1, x2 up to xn, then we multiply by a scalar, the scalar will multiply on each of these elements. So we have the addition and scalar multiplication for the vectors or the elements of r to power n. So we want to see how this one forms a vector space, and possibly we shall need to prove all the 10 axioms for this set here to form a vector space. So let us look at that. So we have these axioms here that we need to prove. One, it is about closure and addition, commutativity and addition. All these ones here, we must show that these ones satisfy. So what we shall do, let us look at basically how we can prove that. We begin, we shall say, we shall first of all let our elements, let, for example, x, which is having the form x1, x2 up to xn, be an element of r to power n. Similarly, we can also let y to be of the form y1, y2. Remember, y is an element of r to power n, so it will be of this form. We need about 3 vectors. Let us have another one, which is, for example, z. So if we let z to also be an element of r to power n, so it means z will be of this form, and also this is an element of r to power n. So we have x, y, and z picked from. It means that x, y, and z are elements of r to power n. So we also need some scalars. We shall pick some few scalars, for example, alpha and beta, to be the elements of r. So we are picking the scalars from a set of real numbers and vectors from r to power n. So we need to show that r to power n forms a vector space. So we shall show that in order to prove, we shall say in order to show that r to power n is a vector space, in order to show that r to power n is a vector space, then we shall need to show, we must show that the axioms, or the axioms here, so the axioms hold. We must show that all the axioms that we are having here, that is u plus v is equal to v plus u, all of this must hold. So let us begin with axiom number 1. So for axiom number 1, from here, it is the closure under addition. So we shall need to show, that is axiom number 1, which we need to prove. We show that r to power n is closed. R to power n is closed under addition. That is closure under addition. That is our axiom number 1 that we must show. So let us consider x plus y. We have seen that x and y are picked from r at power n. So let us consider x plus y. We want to show that x plus y is an element of r at power n. So what is x plus 1? I will arrange this in a column form. So let us have this in column form, x1, x2 up to xn. So we shall add there y1, y2 up to yn. So what is this one equivalent to? Can we say that this is equivalent to, according to the vector addition, we add the corresponding elements. So x1 plus y1, x2 plus y2, and this continues up to xn plus yn. So, but what clearly does this one show? Can we see that all these ones here are also n elements? Because this, when you get x1 plus y1, you will get a value because x and y are real numbers. So it is like when you're having 1 plus 2, you will get a 3. So x1 plus y1, x2 plus y2. So clearly this shows that these elements are elements of r to power n because there are n of them. There are n entries. So clearly we can see that the sum is actually a vector. A sum is a vector with n entries. We can easily see that this sum here has got n entries. That is x1 plus y1, x2 plus y2, up to xn plus yn. Has got n entries, and that is clear. It is therefore clear that it is in r to power n because there are n entries there. So what does this one mean? This one implies that x plus y is actually an element of r to power n. So this vector that is r to power n is closed under addition. So when you get this, this will imply that r to power n is closed under addition. So this will be the proof for axiom number 1. We shall now come to axiom number 2. We now prove axiom number 2. That is, we need to show that u plus v is same as v plus u, or we need to talk about commutativity under addition. So remember, for us we are dealing with x, y, and z. These are our vectors from r to power n, and they are defined as this: x1 up to xn, y1 up to yn, z1 up to zn. So looking at axiom number 2, we need to show that addition is commutative. We need to show that addition is commutative. So for that case, let us consider x plus y. Remember, our x is x1, x2 up to xn, and we are adding y1, y2 up to yn. So using the definition of addition, you need to add the corresponding elements. So we shall add x1 with y1, that is x1 plus y1, that is x2 plus y2, that is xn plus yn. Now, we can as well write this. Remember that x and y are real numbers. These x1, xi's are real numbers. They are picked from a set of real numbers. But we also know that if, for example, you are adding two real numbers, if you have 1 plus 2, it is same as 2 plus 1. If you are dealing with 1.5 plus 0.5, it's same as 0.5 plus 1.5. So when you are dealing with real numbers, we say that for real numbers, here we can say that for real numbers, then it is possible that a plus b is same as b plus a. So similarly, if x and y are real numbers, we can still write y1 plus x1, can still write y2 plus x2. Then we can write yn plus xn. We can easily write it. So for this case, we can easily say that this is same as having y1, y2 up to yn. Adding there x1, x2 up to xn. When we look at that, it is clear that this one here is y and this one here is x. So clearly we can say that x plus y is actually same as y plus x. Therefore, addition of vectors in R to the power n is commutative. We look at axiom number 3. Axiom number 3 is about associativity and addition. So let us consider, for this case, let us consider our x, y, and z picked from R to the power n. So we have already defined all this. We have already defined x, y, and z here. So I will use x, y, and z since we are interested in associativity. So we must have three vectors picked from R to the power n. So for that case, we shall consider x, y, and z. So we shall say we need to prove, we will show that addition of vectors in R to the power n is associative. That is what we need to show. And we shall consider x plus y plus z. What is this one say equivalent to? It is equivalent to having x, which x is x1, x2 up to xn, plus y is y1, y2 up to yn. So what we get here, we shall be adding there z. Our z is z1, z2 up to zn. So what do we get here? We shall be having x1 plus y1. This will be giving us x1 plus y1, x2 plus y2 up to xn plus yn. Adding there Z1, Z2 up to Zn. So, but we know that if we are adding these two again, we can still again say that this one here is same as, we can still say that this one here is same as getting x1 plus y1 plus z1. Still, this one is same as x2 plus y2 plus z2 up to xn plus yn plus zn. We can do that. But still I can say that this is same as having, if I'm adding this plus this again plus this, can we still say that this is same as adding x1 together with y1 plus z1, since x, y, and z are what we call real numbers. So we are adding real numbers. So if I'm having 1 plus 2, 1 plus 2 plus 3, I add 1 plus 2 to get a 3 plus 3. It is also same as getting 1 plus 2 plus 3. So the answer will be the same. So similarly, we are doing the same here. So we are saying this is same as having x2 plus, you can write this as y2 plus z2. Then the trend will continue up to xn plus yn plus zn. That is what we shall have. So similarly, from writing this, we can still say this is same as having x1, x2 up to xn. Adding there, when I have this, I can say this is same as having y1 plus z1, y2 plus z2 up to yn plus zn. We can clearly see that this is same as, this is still same as having x1, x2 up to xn plus, I have this as still, I can open one bracket here. I say this is same as writing y1, y2 up to yn, adding there z1, z2 up to zn. So, but when you look at this one here is same as x plus bracket, this one here is same as y plus this one here is same as z. So what clearly can we say? We can clearly say that x plus y plus z is actually same as x plus y plus z. And if that is true, if this is true, then we can easily say that addition of vectors is associative. Therefore, addition of vectors in R to power n is associative. And that property will as well be proved. Let us now talk about 4, which is about additive identity. So number 4, we need to show the existence of an additive identity. So let us show the existence of an additive identity. So as you all know from what we said last time, there is a vector in V denoted by 0 called the 0 vector, such that when you add that 0 vector together with u, you will get, it will be same as 0 plus u, which is same as u. So we need to show that the 0 vector exists, and we shall prove that. First, we shall let the 0 vector, we know a 0 vector in R to power n. The 0 vector in R to power n is same as 0, 0 up to 0. This is the 0 vector in R to power n. So let us have that one. Let the 0 vector be this one here. So this will imply that when we get, for example, x, so let us also consider x picked from R to power n plus a 0 vector, we shall be having x is x1, x2 up to xn. So on this we are adding there a 0 vector which is 0, 0. So still you will be adding the corresponding terms or elements, x1 plus 0, x2 plus 0 up to xn plus 0. So this one here will be same as again having, when you add x1 plus 0, this x is a real number. If you get a real number, for example 3 plus 0, it will remain as 3. So likewise, when we are considering x1 plus 0, it will remain x1. So we shall have x1, x2 plus 0 will remain x2, and the same up to xn. It is clear that x plus 0, you are also getting what? You are also getting x. So this clearly shows that the 0 vector which is 0 is an additive identity, because for it to be an additive identity, it has to satisfy the condition that when you get x plus 0, it must give you x. And clearly we have seen, if we let our 0 vector to be 0, 0, 0, it is when we shall achieve this condition. So clearly it implies that the 0 vector 0 is an additive identity. In case you don't know how this one, you can easily get this one. You can easily first consider this case here, because this is your interest. This is what you need to prove. So you need to show that x plus 0 is equal to x, which is same as 0 plus x as well. So if you know that you need a 0 vector such that you get x equaling to x, then clearly you can make this one the subject by bringing this one the other side plus negative of x. So clearly you will be able to get your 0 vector, which will be of that form of 0, 0 up to 0. So we have seen that the 0 vector 0 is an additive identity. Axiom number 5, we need to show the existence of an additive inverse. And that additive inverse says that if we consider an element u from V, there exists a vector denoted by negative of u, such that when you get u plus negative of u, you will be getting 0, which is same as having negative u plus u. So that is what we need to prove. So we need to prove the existence of additive inverse. As we have seen, we can say that we first rate, for example, negative of x. What do you think negative of x will be? The negative of x is same as negative of each element of x, negative x1, negative x2, up to negative xn. So let us now consider what will be x plus negative of x. We need to show that when you get x, you add there negative of x, you get the additive identity. But our additive identity was 0. So we need to let our additive inverse to be in such a way that when we get x plus negative of x, we shall be able to get a 0. So you will only be able to get a 0 if this value here is a negative of this. So that's why we have first rate negative of x to be this. And we want to show that this one is true. So we have x plus negative x is same as our x is x1, x2 up to xn. So here we are considering our x, which is picked from r to power n. So we shall add there negative of x1, negative of x2 up to negative of xn. This one here will be same as x1 plus negative of x1, x2 plus negative of x2, and up to xn plus negative of xn. So clearly, we shall be able to get x1 plus negative of x1. It will be giving us 0. This will be 0 up to 0. So looking at this, we can clearly see that x plus negative of x is giving us 0, which 0 is this vector here. So if this is true, we can now therefore say that negative of x is an additive inverse. So clearly we have seen that when you let negative of x to be this, it is when you will be able to get the x plus negative of x equaling to 0. This is what we needed to prove, and clearly we have proved that this one here plus 0, you will get plus negative of x, you will get 0, of which 0 is our additive identity. So this will be proved as well. We now come to axiom number 6. Now we are done with axioms related to addition. We want to now to come to axioms related to scalar multiplication. And to begin with, we need to prove that a closure under scalar multiplication holds. We need to pick one scalar and a vector, then we see whether that scalar times a vector is also an element of that given space. So to do that, we shall be considering x y and z to be picked from r to power n, as we have done, and alpha beta to be picked from r. So what do we need? We are looking at number 6. We need to show that r to power n is closed under scalar multiplication. And for that case, we need to show we need to show that alpha times x is an element in R to power n. As alpha is an element of R, and we are picking x from R to power n. So we also need to show that this one is an element of R to power n. To show that, we shall first of all consider alpha x, and alpha x is same as alpha into x, x1, x2 up to xn. And this is same as, this is alpha, which is outside, this is x1, x2 up to xn. By definition of scalar multiplication, we multiply alpha with x1, we multiply alpha with x2, we multiply alpha with xn. But because alpha is a real number and x is also picked from Rn, but x1, x2 up to xn are real numbers, so you are getting a real number. The xi's, remember, are picked from R, and alpha is also picked from R. So when you get a real number multiplied by a real number, automatically you'll get a real number. So these are real numbers, but which real numbers are having n entries? These are n entries. This one up to this one here. So they are n entries. So clearly, if these are n entries, then it means they are in R to power n. So from here, we can therefore say that alpha times x is an element of R to power n. Since ax has n entries, since ax is a vector, let us say is a vector that has n entries. If it is a vector that has n entries, then automatically it will be an element of R to power n. And for that case, it means that R to power n is closed under scalar multiplication. Therefore, R to power n is closed under scalar multiplication. And you will have proved that. Now we need to prove axiom number 7, which is for each element uv picked from V, a scalar picked from F, you need to show that k into u plus v same as ku plus kv. But since we are dealing with R to power n instead of v, u and v, that is our x and y. Scalars, we are using alpha and beta, so it will be same as having alpha into x plus y. So we need to show that this one here is same as alpha x plus alpha y. So this is what we need to show. So if we need to show that, we shall first of all consider alpha into x plus y. This will be same as alpha into x. Our x is x1, x2 up to xn. You are adding there y1, y2 up to yn. So this will be same as alpha into, when we deal with addition of this one here, will be x1 plus y1, x2 plus y2 up to xn plus yn. So we can as well write this as this is alpha into x1 plus y1. When you add this x1 plus y1 and you multiply by a scalar, then it will be same as alpha into x1 plus y1, alpha into x2 plus y2, up to alpha into xn plus yn. Now, from here, if you multiply alpha into x1 plus y1, it will be same as having alpha x1 plus alpha y1, alpha x2 plus alpha y1, y2, up to alpha xn plus alpha yn. But still this can be written as, when you look at this, we can easily split this one here to give us alpha x1, alpha x2, up to alpha xn. You can add there, still this is alpha y1, alpha y2, up to alpha yn. And this is same as, when you look at this is same as having alpha into x1, x2, up to xn. And this is same as having alpha into y1, y2, up to yn. And what will this one be? This is same as having alpha, but what is this? This is same as x. This is alpha. What is this? This is same as y. So it is clear. It's clear that when you get alpha into x plus y, you get alpha x plus alpha y. And this is your proof. Now, in order to prove axiom number 8, you need two scalars, a and b, and one vector. So you need to prove that a plus b into u is same as a times u plus b times u. So we shall consider x picked from r at power n. We shall consider alpha and beta picked from our field R. So we need to prove so we wish to prove this, and for that case we shall consider alpha plus beta into x, which is same as alpha plus beta multiplied by x, but we know x is same as x1, x2, up to xn. And this can be as well written as, since this is a scalar, alpha plus beta is a scalar, so it is multiplying into x1. By definition of a scalar, we shall multiply alpha plus beta into x1, alpha plus beta into x2, and we shall do the same alpha plus beta into xn. That is by definition for scalar multiplication. So this will be same as having, if I have this, I can easily expand that as alpha x1 plus beta x1, alpha x2 plus beta x2, and I will do the same up to alpha xn plus beta xn. But if I have this, I can still write this as alpha x1, alpha x2, up to alpha xn. Adding there beta x1, beta x2 up to beta xn. So when I look at this, I can easily write this as alpha into x1, x2 up to xn. I can easily write this as beta into x1, x2 up to xn, which is actually same as alpha x plus beta x. So this is x, this is y, this is also x. And that will be proved. Now for axiom number 9, it is A into BU is same as AB into U. That is for any scalars A and B and U into V. So we need two scalars still and one vector in order to prove this. So we shall say that we wish to prove, for number 9, we wish to show that alpha into beta of x will be same as alpha beta into x. So that is what we need to prove. For x, which is picked from r to power n, alpha, beta are picked from our field R. So let us start with alpha into beta of x, and this will be same as having alpha into beta of x is same as beta x1, beta x2 up to beta xn. We can have this as, this is a scalar, so it will multiply into each of these, alpha into beta x1, alpha into beta x2 up to alpha into beta xn. We can still write this as alpha beta times x1, alpha beta times x2 up to alpha beta times xn. We can write it in this form. This is alpha multiplied into this. We can still multiply alpha with beta and it will be the same. So clearly we can easily see that this is same as alpha beta into x1, x2 up to xn. But when we look at this, this will be alpha beta. This one here is x. So clearly alpha into beta x is same as alpha beta into x. Finally, we need to show that 1 times u is same as u for the unit scalar 1 picked from f. So for this case, we are having, that is 10. Finally, we need to show that 1 times x is same as x. So our vector is x, which is picked from r to power n. So 1 is picked from our field f. So we need to show this. Let us begin with 1 times x. 1 times x is same as 1 times x1, x2 up to xn. But what is this? This is same as having 1 times x1, 1 times x2 up to 1 times xn. But what is this? This is same as having x1, x2 up to xn. And when you look at this, this is actually same as x. So clearly 1 times x is same as x, and that will be true. So we shall give a conclusion that by the above proofs, or that we have seen, by the above proofs, it is now clear that r to power n satisfies. It is now clear that r to power n satisfies the vector space axioms. Hence, r to power n is a vector space So this will be the proof.